Hello everyone, welcome to this video. In the previous video we saw what is a family of curves for some differential equation. Now in this video let's have a look at some of the examples. Correct? So here I am taking the set of concentric circles which are defined by this equation x square plus y square is equal to c. Right, this c cannot be a negative quantity because it actually has to be the square of some quantity, right? And it should be a real number, otherwise our equation would not remain the same, right? In the previous video, if you remember, we talked about various parabolas of this kind, various upward parabolas, right? So this family of equations, this family of parabolas form the family of solutions for the differential equation. This you already saw in the previous video, right? You found the solutions like this: y is equal to x square plus c, where c was some parameter. This was one parameter family of solutions, correct? So here also, in this case also, you have various circles, concentric circles, in fact, with the center as 0 0, right? X minus 0 square plus y minus 0 square is equal to c, where c is also some real number. It is the square of some quantity. So you see, you have this as the center, and taking this as center, you can draw various circles, right? All of these circles, they are concentric in nature, right? And moreover, all such circles, they form the family of circles. Now here, what thing is varying in this particular kind of circles? The radius is varying. So here you can clearly see that we have only one as the parameter which changes, which is the c, correct? So this forms one parameter family of curves, or the solution of the differential equation. So now, based on this example, can we form a differential equation using this, knowing this as the solution? Can we know what is this, what is the differential equation created from this family of curves? So let's have a look at this kind of problem, correct? So here let's see how do we proceed here. For this, we write our given family of curves as x square plus y square is equal to a square, correct? Now using this, we wanted to get rid of a, we wanted to eliminate a from our equation. So you see, this can be clearly done if you differentiate this differential equation, this normal equation, not differential equation. So what we can do, we can differentiate with x. Usually x is the independent variable with which we can we usually differentiate, and y is the corresponding dependent variable. And until and unless mentioned, we take and use these kind of terminology here, correct? So here we differentiate with respect to x, the independent variable, to obtain the derivative of x with x. The derivative of x square with x is 2x, and dx upon dx is just 1, and you have the derivative of y square as 2y into dy by dx as such, no change, and the derivative of constant is 0. So from here, this 2 and 2 gets cancelled, so you have this as your differential equation. This is a non-linear kind of differential equation. Why? Because the dependent variable y and its derivative, they are present in the product form, correct? So this is the required differential equation, and this parameter, one parameter family of curves, is basically the solution to this kind of equation. You can also verify this thing by substituting the value of this derivative in y into this equation, and then simplifying to obtain the value of left hand side as equal to 0 as well, correct? So you can try this thing. Okay, moving forward, we can have a look at another kind of curves, which is y is equal to e raised to power x a cos x plus b sin x, right? Where both a and b are two arbitrary constants. This is a two parameter family of curves. Why? Because here we have two arbitrary parameters involved with this kind of equation, right? This is an exponential sinusoidal kind of wave which you usually study in physics, right? So here relating to this, we have a question that states that find the differential equation of the family of curves given by this equation where both a and b are the arbitrary constants. So let's just the process is the same. Let's just copy down our equation, the given family of curves, like this. Now here we have two constants, so we have to eliminate both of them. So we have to differentiate this equation one. How many times? We have to differentiate it twice, right? Because we wanted to get rid of these two constants. So differentiating it once, we obtain this kind of equation. Here we have to apply the product rule when we are differentiating this equation with respect to x. Both this term and this term contains x. So first time this term is as such, we have performed the derivative of this term. Next we have kept this term as such and perform the derivative of e to the power x, which is the same quantity, correct? Now if you see what is this thing, this is just y, so you can replace this quantity with y here, and then you can further differentiate this equation to obtain the second derivative. So on the left hand side you obtain the second derivative. Here again you have to apply the product rule, first term as such, the derivative of this term, and then the second term as such, the derivative of e to the power x is e to the power x, and the derivative of y is dy by dx. Now notice that if you take negative common from this, it would be e to the power x a cos x plus b sin x, correct? So what is this kind of equation? This was the initial equation from which we started, and this is y. So you can replace this thing with y here. So because we wanted to get rid of these quantities here, because we do not want a and b here, so we can write whole of this thing as minus y, correct? And so we have one term here, this as this. What about the next? We also wanted to get rid of this thing. So can you see this thing somewhere? Yes, in equation 2. So from here you can substitute the value of this quantity as dy upon dx minus y. This thing is equal to this expression, correct? So you can substitute in place of this quantity the value dy by dx minus y plus dy by dx as such, correct? So you can simplify this, and your required differential equation is the second order differential equation where you have your second order derivative d2y by dx2 minus 2 dy by dx plus 2y, that is equal to 0, correct? Now let's move forward and have a look at our third example. Here in this example we have a 3-parameter family of curves. Now this would include 3 different arbitrary constants. So this is the set of circles. Now here we are taking arbitrary circles. One circle is here, one is here, one is having bigger radius, one is having smaller radius, and so on. So radius is also arbitrary, and the centers x and y coordinate, they are also arbitrary in nature. So therefore it is a 3-parameter family of curves. Now I give you an exercise to create a differential equation of this parameter family of curves. So that means for this parameter, this family of curves, you have to differentiate it 3 times. Why? Because you have 3 different arbitrary constants present within this equation, and out of those 4 equations, those 3 and this one, you have to eliminate these and form an equation present within the derivatives. So that would be your differential equation. If you have any doubt, this is your question. This is an exercise which I am leaving up to you, right? If you have any doubt, you can note down these rules and follow them in order to calculate the results. So the rules are, if you wanted to create the differential equation from the given equation in x and y, which contains n, in general I am taking n arbitrary constants, then you first of all write down the equation of the family of the curves which is given to you. Mark this as equation 1. This is your first equation. Then you can differentiate this equation how many times? N times, to get n new equations, right, which contains n arbitrary constants, the previous constant only, with their derivatives, with the derivatives of the dependent quantity. So in total you have one equation here and n equations here. So in total you have n plus 1 such equations, right? So out of those n plus 1 equations, you now have to eliminate those n arbitrary constant. You can apply any method to do that, right? So once you have performed that step, once you have eliminated all the n arbitrary constants out of these n plus 1 equations, your required differential equation would be present in front of you, which would be an nth order differential equation. Correct? So I hope you understood this concept of forming differential equation. You got an idea of how we can create different family of curves, right? How does they look like? How do they look like? And you can try this exercise by yourself to get a better view of this concept. So I hope you understood this concept well. Well, that is it for this video. Thank you for watching.